So imagine you're holding I don't know, a titanium bone screw.
Right, something incredibly tiny.
Exactly. It's tiny, it's flawless, perfectly threaded, and you just know that if it's off by like even a fraction of a millimeter, the human body is just going to reject it entirely.
Oh, absolutely. Or, I mean, even think about the microscopic fuel injectors inside a high-performance car engine.
Yeah. We encounter these absolutely perfect micrometer accurate metal components literally all the time. But getting a solid, cylinder of raw metal to yield to that level of perfection,
Okay.
that requires a massive violent manipulation of physics.
It really does. It's not gentle at all.
Right. So today's deep dive is an exploration into the hidden mechanics of that extreme precision. We've got a fascinating stack of technical sources today, and we're looking at the inner workings of CNC Swiss-type lathes.
Yeah, and just to kind of put that in context for you, on a traditional lathe, you basically clamp a piece of metal in a chuck, it sticks out into the air, and a cutting tool moves along its length to, carve out a shape.
Which works fine for short, thick things, I guess.
Exactly. But when you're making incredibly long, slender parts, that traditional method completely falls apart. I mean, the metal just bends away from the tool.
So today our mission is zeroing in on the engineering marvel that actually solves this, which is the guide bushing. We want to decode how this specific component prevents solid steel or, titanium or brass from vibrating or deforming while it's being aggressively sheared apart at thousands of revolutions per minute.
Which is a crazy environment when you really picture it.
It is. So let's ground this physically for you. Imagine trying to write a sentence with a really long, freshly sharpened pencil, but you're forcing yourself to hold it all the way back by the eraser.
Oh man, that's impossible.
Right. As soon as you press the tip down onto the paper, the pencil just bows in the middle. The graphite skips, it like chatters across the page.
What a mess.
Yeah. And that bowing is exactly what happens to a long bar of metal inside a machining center when a heavy, really sharp cutting tool hits it.
Yeah. And in the machining world, that bowing is literally called deflection. When a metal bar deflects away from a cutting tool, I mean, even by a microscopic amount, the results are catastrophic for the part.
Because you're trying to be micrometer accurate.
Exactly. You don't just get a sloppy dimensional line. That skipping effect you mentioned with the pencil, that manifests as chatter.
Chatter.
Yeah, it's this bounces off the metal. It leaves this cloudy, shattered-looking surface finish. And you also end up with tapered edges, where the part is physically thicker at one end than the other.
Which means the part goes straight into the recycling bin, I assume.
Oh, instantly.
Yeah.
I mean, if you're manufacturing aerospace connector pins or medical implants, the tolerances are so incredibly tight that a cloudy surface finish isn't just an aesthetic flaw.
It's a functional failure.
Right. It will not work.
So the guide bushing essentially cures this deflection problem, right? Instead of holding the pencil by the eraser, the guide bushing acts as this rigid support collar, and it's placed like a fraction of a millimeter away from the cutting tool.
Yeah, it basically holds the pencil right down by the lead.
Okay, got it. So the bar of raw stock slides through this bushing, and the cutting tool stays locked right next to it.
Precisely. By drastically shortening the unsupported length of the metal bar, the machine neutralizes the leverage the tool has against the material. It guides the radial movement and allows the machine to carve out these incredibly accurate, long, slender geometries.
But, and this is where the sources get really interesting, they make it very clear that one single type of support collar cannot handle the sheer variety of manufacturing demands. I mean, the geometry, the raw material stiffness, the production volumes, all of that changes the physics of the cut entirely.
It changes everything, yeah.
So how do engineers approach the most sensitive jobs, like the really tricky cylinder parts that need to be machined at massive speeds without suffering a single microscopic scratch?
Well, for those, they utilize the rotating guide bushing. This setup is specifically engineered for long, delicate parts. The bushing itself is physically tethered to the machine's main spindle through a complex drive system.
Wait, complex how?
We're talking about a really sophisticated arrangement of secondary shafts, gears, or timing belts.
Oh, wow. So the bushing and the raw metal bar are spinning together as a single synchronized unit.
Yes, which completely neutralizes the relative surface speed. The metal bar isn't sliding against the inner wall of the bushing. I mean, they are moving in perfect unison.
Which eliminates the rotational friction entirely. You don't have metal scraping against metal while it spins at like 10,000 RPM.
Exactly. And the math behind this revolves around the length to diameter ratio, so the LD ratio. The rotating guide bushing is the go-to standard for parts with an LD ratio above 3.
So meaning, if you have a metal shaft that is 10 millimeters thick and you need to cut a profile that is more than 30 millimeters long, you are in rotating bushing territory.
Right, exactly.
Yeah.
And because that relative sliding friction is gone, the machine can run at blistering spindle speeds while protecting highly scratch-sensitive surfaces.
Like the tiny motor shafts or delicate valve stems.
Yeah, medical pins, things like that. Any surface mark on those parts ruins them. So the synchronized rotation protects the outer diameter perfectly.
But wait, I have to push back on this a little bit. Adding a web of secondary shafts, timing belts, and extra bearings to an environment that vibrates violently and is just flooded with cutting fluid that seems incredibly risky.
Though it is.
Like you are introducing multiple new points of mechanical failure just to spin a support block.
And the engineering sources validate that concern entirely.
Mm-hmm.
I mean, the rotating guide bushing is a complex mechanism, and complexity inherently breeds vulnerability. The first trade-off is just a significant increase in baseline maintenance and purchase costs.
Because you have an entirely secondary transmission system that needs constant monitoring.
Yeah, and if a timing belt inside that transmission starts to degrade, you have a massive problem.
Right, because rubber belts in a hot oil don't mix well.
Exactly. The physical reality of belt wear is really unforgiving. As a rubber timing belt ages in a hot, oily machine, the teeth can become polished or they harden. And when they harden, they lose their physical grip on the pulleys.
And if that belt slips?
Even by a fraction of a rotation, you suddenly introduce a speed differential between the spinning bushing and the spinning metal bar. The synchronization breaks.
Oh, and they scrape against each other.
Yeah, in a fraction of a second, the inner wall of the bushing tears a microscopic trench right into the surface of your metal part, instantly destroying it.
That's terrifying. And beyond the belts, the sources detail something called labyrinth seals, protecting the bearings of this rotating assembly. And what is that?
So a labyrinth seal is a mechanical barrier designed to keep contaminants out of the ball bearings that actually allow the bushing to spin. It's not like a standard solid rubber lip.
Okay, what is it then?
It's a tortuous maze-like path of interlocking metal rings. The idea is that the cutting fluid and tiny metal chips have to navigate this incredibly complex physical maze just to reach the bearing.
But if a microscopic flake of, say, titanium actually manages to navigate that maze and get inside the bearing...
Oh, it acts like a microscopic buzzsaw.
Yikes.
Yeah, the ball bearings grind that metal flake down into this abrasive paste. It scores the bearing races, creates immense heat, and eventually just seizes the entire rotating assembly.
That sounds incredibly expensive to fix.
Huh?
And there is also a major material cost hidden in this setup, too. The sources talk about the remnant problem.
Right, the remnant.
Because this rotating assembly is physically bulky. You know, it needs room for the bearings, the pulleys, the housing. It creates a physical distance between the machine's main collet and the cutting tool.
Yeah, and to visualize the main collet for you guys listening, think of it as a segmented metal fist that grips the very back end of the raw bar stock to just push it through the machine.
Right, so you have this metal fist at the back, pushing the bar through the bulky rotating bushing to reach the tool at the front. But when you reach the very end of a, 12-foot bar of raw material, the metal fist can't push through the bushing. It has to stop.
Which leaves a physical bridge of raw metal just stranded between the collet and the cutting tool.
So the machine simply cannot cut that final section.
No. It becomes a remnant, just a piece of wasted material that gets ejected and thrown in the scrap bin at the end of every single bar. And because the rotating bushing assembly is long, that wasted remnant is long.
Wow. So if you are machining aerospace-grade titanium or specialized medical alloys, throwing away inches of material every time you load a new bar is literally bleeding money.
Oh, it adds up so fast.
Which totally begs the question.
Right.
If adding belts introduces transmission failures and the bulky bearings cost you inches of expensive raw material, why spin the bushing at all? Why not just bolt a solid support block to the machine and let the metal spin inside it?
Well, that is the stationary vise approach, which is officially known as the fixed guide bushing. In this configuration, the guide bushing is bolted dead still to the machine casting. It does not rotate at all.
The raw metal bar just rotates rapidly inside a precision ground hole.
Exactly. Also used for long, slender parts with an LD ratio above 3.
But I would imagine the structural rigidity here is completely unmatched. I mean, it's just a solid block of metal holding the part steady with zero moving parts to vibrate or wear out.
Yeah, the precision potential is the highest of any setup because you eliminate all the tolerance stacking of those extra bearings and belts we talked about. But It creates a monumental hurdle in physics.
Because of the friction.
Yes, you are spinning a raw metal rod inside a stationary metal hole at thousands of revolutions per minute under heavy radial cutting pressure.
The friction generated by that has to be staggering. Here's where it gets really interesting to me. It's like trying to hydroplane a car on a wet road, but you are trying to do it perfectly in a circle all day long.
That's a good analogy, but let's refine that physical image a bit because hydroplaning kind of implies a loss of control, right?
Okay, yeah.
A better way to visualize this is an air hockey table, but wrapped 360 degrees around a cylinder. The entire system relies on hydrodynamic lubrication.
Meaning oil.
Yes, a continuous, microscopic film of oil must separate the rotating bar from the stationary bushing wall. The spinning motion of the bar actually physically drags the cutting oil into a wedge shape, generating immense internal fluid pressure.
Oh, wow.
Yeah, and that pressurized oil wedge acts as a solid, frictionless barrier holding the metal perfectly centered in a microscopic hug.
That is wild. The fluid itself becomes the structural support.
Exactly. But if that oil film thins out or collapses, the friction instantly takes over.
And what happens then?
The heat generated will cause the metal bar to expand thermally, which tightens the clearance even more, and you get this runaway thermal feedback loop. You get deep galling, which is metal literally tearing away from the surface, or the friction can friction weld the bar to the bushing.
Oh, man. Destroying the tooling and halting production completely.
Instantly.
So to maintain a fluid barrier that precise, the raw metal sliding into the machine can't just be standard hardware store steel, right?
No, absolutely not. The fixed bushing demands absolute perfection from the raw material. The bars must be centerless ground to exacting tolerances. I mean, they must be perfectly straight and flawlessly round.
Because if a bar has a microscopic lump or like an oval shape to it, what happens to our 360-degree air hockey table?
The fluid dynamics fail entirely. The lump bulges against the stationary bore, violently bursting the pressurized oil film, which leads to immediate metal-on-metal contact.
And a disaster.
Right. The rotating bushing we discussed earlier is slightly more forgiving of raw material imperfections because the bushing physically rotates with the lump. But the fixed bushing forces the fluid barrier to absorb every single geometric flaw.
And structurally, because the fixed bushing is still a physical block sitting between the main collet and the cutting tool, we are still dealing with that wasted material remnant at the end of the bar, right?
We are. The fixed bushing might be slightly shorter than the rotating assembly, but yeah, you are still throwing away a significant chunk of raw material at the end of every production run.
So let's look at the harsh economic reality of this. If a shop is mass-producing millions of tiny threaded spacers out of highly expensive medical alloys, throwing away a remnant on every bar will destroy their profit margins. So how do they eliminate that physical distance between the metal fist holding the back of the bar and the tool doing the cutting at the front?
By removing the middleman entirely, they utilize non-guide bushing mode. The front support collar is completely physically removed from the machine casting.
The rogue option. You just take the bushing out and leave the metal hanging in the air.
Basically, yeah. The machine's main spindle, the part housing that segmented metal fist, the collet, slides all the way forward. The collet itself becomes the sole source of support, presenting the raw material mere millimeters away from the cutting tool.
Okay, so going back to our pencil analogy, you are holding the pencil by the eraser again, but you just make the pencil incredibly short.
Exactly. Because you've eliminated the physical bulk of the guide bushing, the main collet can push the very end of the bar right up to the cutting zone. The wasted remnant length drops drastically, sometimes down to just 30 millimeters.
Which is tiny. Over a high-volume production run of expensive titanium, that material savings translates to massive financial retention.
Huge savings. But if we connect this to the bigger picture, physics demands a trade-off. Without that front support collar taking the radial pressure of the cut, the deflection problem comes roaring back.
Right, because there's nothing holding the tip.
Which restricts this mode entirely to short parts. The LD ratio rule flips here. Non-guide bushing mode is strictly for parts with an LD ratio below 3. So nuts, spacers, washers, short structural connectors.
Because if you attempt to machine a long medical pin in this mode, the excessive overhang turns into a lever.
Yes. The cutting tool pushes on the far end of the part bends, and you get that violent chatter we talked about.
The tool bounces off the material, shattering the cutting edge.
Exactly. But the damage goes deeper than just a ruined part. When you have a guide bushing in place, the immense radial force generated by slicing through solid metal is absorbed locally by that support block. When you remove the bushing, That heavy cutting load travels down the length of the metal part and directly into the machine's main spindle bearings.
Oh, wow. The bearings spinning the metal fists are suddenly taking heavy lateral hammer
You
blows.
got it. You are dramatically extending your material yield, but you are asking the core rotational components of the machine to absorb a significantly higher volume of punishment. Over time, that accelerates bearing wear.
Man. So if the variables are this intense, balancing belt wear against friction welding and material savings against bearing destruction, how does an operator actually decide which physical setup to commit to? I mean, deciding between these three modes sounds terrifyingly permanent.
Well, the good news is modern machines actually allow conversion between guide and non-guide modes for mixed orders. It's not totally permanent, but deciding. The LD ratio of 3 is merely the starting line. An operator must synthesize a complex matrix of variables.
Like what?
Well, what is the molecular hardness of the alloy? How deep is the cutting tool plunging into the material? What is the specific geometry of the tool edge? I mean, a short part carved from a fiercely hard superalloy might generate such aggressive cutting resistance that the material deflects, forcing the operator to use a guide bushing despite the short length.
Right. Conversely, you could have a longer part made of like soft brass where you are only shaving off a microscopic layer and the cutting forces are so light it remains perfectly stable without a bushing.
Exactly. The only way to know definitively is to basically command the physics in the real world. Operators perform trial cuts, they set the machine, execute the tooling path, and then meticulously measure the resulting geometry for microscopic diameter changes, taper, and roundness.
That sounds intense.
They even monitor the main spindle housing temperature with thermal probes to ensure the bearings aren't overheating from the strain of a non-guide setup.
So the daily reality of maintaining these tolerances sounds completely relentless. The maintenance breakdowns in the sources highlight just how precarious this precision is. With the rotating bushing, they are hunting for polished teeth on those timing belts every single day to catch a microslip before it ruins a batch of parts.
Yeah, and they are inspecting those labyrinth seals with magnification, ensuring not a single sliver of metal has breached the physical maze protecting the bearings.
And the maintenance for the fixed bushing sounds even more nerve-wracking to me. The stationary bore has to be cleaned of microscopic debris every single shift. If this bore demands absolute perfection to maintain that 360-degree fluid barrier, how do you even clean it? One scrape from a standard tool, and the geometry is ruined.
Well, that is a huge point. That is exactly why operators are strictly forbidden from using hardened steel picks or standard wire brushes to clear out the stationary bore.
Right, the source explicitly mentioned this. You cannot use hard steel picks to clean a precision bore.
No, you have to use specialized soft brass or non-metallic, non-scratching picks. The internal surface finish of that bore is paramount to maintaining the hydrodynamic oil wedge.
Because one impatient moment, an operator tired at the end of a shift, digging a stuck chip out with a steel screwdriver, it scores the inside of the bore.
And the fluid dynamics break, the oil film collapses, and the next part friction welds inside the machine.
Ah, unbelievable.
And beyond the cleaning discipline, the operator must visually confirm the fluid timing. They have to verify that the pressurized oil delivery system is actively coating the bore before the spindle ramps up to production speed.
So if they initiate the cutting cycle and the oil delivery is even a second late,
The dry friction instantly destroys the setup.
wow. And for the non-guide mode, where the main collet is absorbing all that lateral punishment, the maintenance focus shifts to the metal fist itself, right?
Correct. They constantly monitor the clamping force and check the collet for runout, which is any microscopic wobble in the rotation caused by bearing fatigue. Most critically, they have to maintain vigilance against chip buildup around the clamping mechanism.
Because if fine metal dust infiltrates the slots of the collet, it prevents the fist from closing completely.
Yeah, the metal bar isn't clamped with enough pressure, and when the cutting tool hits it, the solid rod just physically slips backward into the machine.
Ruining the dimensional length of the part and potentially crashing the tooling.
Exactly.
So what does this all mean? When you synthesize all these mechanical realities, the flawless finish on a medical implant or a high-performance engine component, it stops feeling like standard manufacturing.
It's definitely not standard.
It is a grueling daily orchestration of trial cuts, relentless maintenance, and perfectly calibrated friction.
Yeah, a guide bushing's fundamental mandate is just to fight deflection by providing near-point support and choosing between a rotating dancer, a stationary fluid vise, or running the raw, unsupported non-guide mode. It requires engineers to constantly balance physical rigidity against cutting speed, surface finish requirements, and the harsh economics of material waste.
It fundamentally changes how you look at a simple threaded screw. And looking toward the future of this technology, the sources note that as aerospace and medical fields demand even harder, more exotic superalloys, the cutting forces required will continue to escalate.
Pushing the physical limits of that 3-to-1 LD ratio even further.
Exactly, which raises a fascinating engineering challenge that I wanted to leave you guys with. Will the physical limitations of microscopic fluid barriers and synchronized rubber belts eventually force the industry to abandon physical contact entirely?
Hmm.
Could we see a future where solid metal is supported radially by frictionless, high-frequency magnetic levitation while it's being cut?
Utilizing focused magnetic fields to provide infinitely stiff, near-point radial support without a single point of physical contact. It sounds like science fiction today.
It totally does.
But given the relentless physics of friction and deflection we've discussed, magnetic near-point support might be the exact paradigm shift required to machine the alloys of tomorrow.
A completely frictionless guide bushing. I mean, I will certainly be watching the machining world to see if someone cracks that code.
It would change everything.
It really would. Well, thank you for joining us on this deep dive into the mechanics of precision. The next time you rely on the flawless operation of your vehicle or a piece of medical technology, just take a moment to appreciate the violent, microscopic balancing act of physics that made it possible. Keep wondering, keep exploring, and we'll see you next time.